Machines. Syllabus. Machines as force multipliers, load, effort, mechanical advantage, velocity ratio and efficiency, simple treatment of levers, pulley systems showing the utility of each type of machine. Scope of syllabus, functions and uses of simple machines, terms, effort E, load L, mechanical advantage MA is equal to L upon E, velocity ratio VR is equal to VE upon VL is equal to DE upon DL, input WI, output WO, efficiency eta, relation between eta and MA, VR, derivation included. For all practical machines, eta less than 1, MA less than VR, lever, principal, first, second and third class of levers. Examples, MA and VR in each case. Examples of each of these classes of levers as also found in the human body. Pulley system, single fixed, single movable, block and tackle, MA, VR and eta in each case. A. Machines, technical terms and levers. Machines. It is a common experience that it is easier to open a nut by the use of a wrench than to open it by hand. It is difficult to pull up a bucket of water directly from a well, but it becomes much easier to pull it up with the use of a pulley. It is difficult to shift a heavy block by pushing it, but it becomes easier to shift it by using a crowbar. We can find many such examples in our daily life where the use of a machine such as the wrench, pulley, crowbar, etc. makes the job easier. Functions and uses of simple machines. The various functions of machines are useful to us in the following 4 ways. 1. In lifting a heavy load by applying the less effort, that is, as a force multiplier. Examples, a jack is used to lift a car, a bar is used to lift a heavy stone, a spade is used to turn the soil, pulleys are used to lift a heavy load, a wheelbarrow is used to carry a load. In all these examples, the effort is much less than the load, so the machine acts as a force multiplier. 2. In changing the point of application of effort to a convenient point. Example, the rear wheel of a cycle is rotated by applying the effort on the pedal attached to the toothed wheel, which is joined to the rear wheel with the help of a chain. Thus, the point of application of effort is changed from the pedal to the rear wheel. Functions and uses of simple machines. 3. In changing the direction of effort to a convenient direction. Example, if a bucket full of water is lifted up from a well without the use of a pulley, effort has to be applied upwards. By using a single fixed pulley, it becomes possible to lift the bucket from the well by applying the effort in the downward direction instead of applying it upwards. Thus, the person lifting the bucket up may also use his own weight as effort. 4. For obtaining a gain in speed, that is a greater movement of load by a smaller movement of effort. Examples. First, when a pair of scissors is used to cut the cloth, its blades move longer on cloth while its handles move a little. Second, the blade of a knife moves longer by a small displacement of its handle. Here, the effort is more than the load. Hence, we define a machine as below. A machine is a device by which we can either overcome a large resistive force or load at some point by applying a small force or effort at a convenient point and in a desired direction, or by which we can obtain a gain in speed. Note: a machine cannot be used as a force multiplier as well as a speed multiplier simultaneously. For a machine used as a force multiplier, effort is less than load, while for a machine used to obtain gain in speed, effort is greater than load. Technical terms related to a machine. 1. Load. The resistive or opposing force to be overcome by a machine is called the load, L. 2. Effort. The force applied on the machine to overcome the load is called the effort, E. Mechanical advantage of machine. The ratio of the load to the effort is called the mechanical advantage of the machine. That is, mechanical advantage, or MA, is equal to load, L, upon effort, E. So MA is equal to L upon E. Let this be equation 1. In a machine used to overcome a certain load, if the effort needed is less than the load, the machine has the mechanical advantage greater than 1, while if it needs an effort greater than the load, it has the mechanical advantage less than 1. A machine has the mechanical advantage equal to 1 if the effort needed is equal to the load. A machine having the mechanical advantage greater than 1 works as a force multiplier, while the machine having the mechanical advantage less than 1 gives the gain in speed. The machine having the mechanical advantage equal to 1 is generally used to change the direction of effort, as there is no gain in force or speed. Since mechanical advantage is a ratio of two similar quantities, so it has no unit. Velocity ratio, VR. The ratio of the velocity of effort to the velocity of load is called the velocity ratio of machine. That is, velocity ratio, VR, is equal to velocity of effort upon velocity of load. If dl and de are the distances moved in the same time t by the load and the effort respectively, then velocity of load is equal to dl upon t. Velocity of effort is equal to de upon t. Then velocity ratio VR is equal to de upon t upon dl upon t, which equals de upon dl. Or VR is equal to de upon dl. Let this be equation 2. Thus, the velocity ratio is also defined as the ratio of the displacement of effort to the displacement of load. A machine in which the displacement of load is more than the displacement of effort will have the velocity ratio less than 1, and such a machine gives the gain in speed because load is moving at a faster rate. On the other hand, if the velocity ratio of machine is more than 1, that is, the displacement of load is less than the displacement of effort, the machine acts as a force multiplier. The velocity ratio of a machine is 1 if the displacement of load is equal to the displacement of effort. Such a machine generally changes the direction of effort. Unit. Since the velocity ratio is also the ratio of two similar quantities, distances, so it has no unit, just like mechanical advantage. Technical terms related to a machine. 5. Work input. The work done on the machine by the effort is called the work input, W input. That is, work input is equal to work done by the effort. Let this be equation 4. 6. Work output. The work done by the machine on load is called the work output, W output. That is, work output is equal to work done on the load. Let this be equation 5. 7. Efficiency, eta. Efficiency of a machine is the ratio of the useful work done by the machine to the work put into the machine by the effort. In other words, efficiency is the ratio of the work output to the work input. It is denoted by the symbol eta. Thus, efficiency is equal to work output upon work input. But efficiency is usually expressed as a percentage, so we may write efficiency is equal to work output upon work input into 100%. Let this be equation 6. Efficiency has no unit since it is also the ratio of two similar quantities, that is, work. Note, due to first, friction, and second, weight of the moving parts of a machine of a given design, its velocity ratio does not change, but its mechanical advantage decreases, and so its efficiency decreases. Principle of a machine. When energy is supplied to a machine by applying the effort, it overcomes the load by doing some useful work on it. The point at which the energy is supplied to a machine by applying the effort is called the effort point, and the point where the energy is obtained by overcoming the load is called the load point. Input energy is equal to work done at the effort point is equal to effort into displacement of the point of application of effort. Output energy is equal to work obtained at the load point, which equals load into displacement of the point of application of load. For an ideal machine, output energy is equal to input energy. Let this be equation 7. The useful work done by a machine, that is output energy, can never be greater than the work done on the machine, that is input energy. Otherwise, it will violate the principle of conservation of energy. Therefore, no machine can ever have efficiency greater than 1, that is more than 100%. Ideal machine. An ideal machine is that in which there is no loss of energy in any manner. Here, the work output is equal to the work input. That is, the efficiency of an ideal machine is 100%. Actual machine. In an actual machine, the output energy is always less than the input energy. That is, there is some loss of energy during its operation. The loss of energy in a machine is due to the following 3 reasons. 1. The moving parts in it are neither weightless nor smooth or frictionless. 2. The string in it, if any, is not perfectly elastic. And 3. Its different parts are not perfectly rigid. Note: the most prominent loss in energy is in overcoming the force of friction between the moving parts of a machine. The energy so lost appears as heat, due to which the moving parts of machine get heated. If a machine is 80% efficient, it implies that 80% of the total energy supplied to the machine at the effort point is obtained as useful energy at the load point. The remaining 20% of the energy supplied is lost in overcoming the force of friction, etc., and it appears as heat energy in its different parts, due to which they get heated up. Relationship between efficiency and mechanical advantage and velocity ratio. Let a machine overcome a load L by the application of an effort E. In time t, let the displacement of effort be dE and the displacement of load be dL. Work input is equal to effort into displacement of effort, which equals E into dE. Work output is equal to load into displacement of load, that is L, into dL. Efficiency, we know, is equal to work output upon work input, or efficiency is equal to L into dL upon E into dE, which equals L upon E into dL upon dE. Further, L upon E into 1 upon dE upon dL. But L upon E is equal to MA, mechanical advantage, and dE upon dL is equal to VR, velocity ratio. Therefore, efficiency is equal to MA upon VR, or MA is equal to VR into efficiency, eta. Let this be equation 8. Thus, the mechanical advantage of a machine is equal to the product of its efficiency and velocity ratio. Note: for an ideal machine, free from friction, etc., work output is equal to the work input, so the efficiency is equal to 1 or 100%, and the mechanical advantage is numerically equal to the velocity ratio. In actual practice, the mechanical advantage for all practical machines is always less than its velocity ratio. That is, MA is less than VR, or the output work is always less than the input work, so the efficiency is less than 1. That is, eta is less than 1. Due to some loss of input energy against the force of friction, etc. Levers. Levers are the simplest kind of machines used in our daily life. A lever is a rigid, straight or bent bar which is capable of turning about a fixed axis. The axis about which the lever turns passes through a point of the lever which is called the fulcrum. It is generally marked by the letter F. This point does not move but remains fixed when the lever is in use. Principle of a lever. MA of a lever. Figure shows a lever or a straight rod, AB, with the fulcrum at F. At point E, applied at a point A of the lever, overcomes a load L at the point B. From the fulcrum F, the distance FA to the point A at which the effort is applied is called the effort arm, and the distance FB of point B at which the load acts is called the load arm. For an ideal lever, it is assumed that the rod is weightless and there is no friction at the fulcrum. A lever works on the principle of moments, according to which in the equilibrium position of lever, moment of load about the fulcrum must be equal to the moment of effort about the fulcrum, and the two moments must always be in opposite direction. Moment of load L about the fulcrum F is clockwise, while the moment of effort E about the fulcrum F is anti-clockwise. Thus, clockwise moment of load about the fulcrum is equal to anti-clockwise moment of effort about the fulcrum. That is, load into load arm is equal to effort into effort arm. L into FB is equal to E into FA. Or L upon E is equal to FA upon FB. Let this be equation 9. But from equation, L upon E is equal to MA. Therefore, MA is equal to effort arm FA upon load arm FB. Let this be equation 10. This relation is known as the law of levers. Thus, the mechanical advantage of a lever is equal to the ratio of the length of its effort arm to the length of its load arm. From equation 10, it is clear that 1. If effort arm is equal to load arm, MA is equal to 1. 2. If effort arm is greater than load arm, MA is greater than 1. And 3. If effort arm is less than load arm, MA is less than 1. Obviously, the mechanical advantage of a lever can be increased either by increasing its effort arm or by decreasing its load arm, that is by shifting the fulcrum towards the load. Kinds of levers. Depending upon the relative positions of the effort, load, and fulcrum, there are following 3 types of levers. 1. Class first levers. 2. Class second levers. And 3. Class third levers. 1. Class first levers. In this type of levers, the fulcrum F is in between the effort E and the load L, as shown in figure. Note that the fulcrum F need not be at the midpoint between the load L and the effort E, but the load and effort are on either side of fulcrum in the same direction. Examples: a seesaw, a pair of scissors, crowbar, handle of water pump, claw hammer, pair of pliers, beam of a physical balance, spade used for turning the soil, spoon used to open the lid of a tin can, catapult, and nodding of the human head are the few examples of class first levers. For class first levers, the mechanical advantage and velocity ratio can have any value either greater than 1, equal to 1, or less than 1. When the effort arm is longer than the load arm, the mechanical advantage and the velocity ratio of the ideal class first lever are greater than 1. Such a lever serves as a force multiplier, that is, it enables us to overcome a large resistive force, load, by a small effort. For example, shears used for cutting the thin metal sheets have much longer handles as compared to its blades. Similarly, a crowbar, claw hammer, pliers, and spoon used to open the lid of a container have long handles or long effort arm. If an ideal class first lever has effort arm and load arm of equal lengths, then both its mechanical advantage and velocity ratio are equal to 1. For example, A physical balance with both arms equal in length has mechanical advantage and velocity ratio equal to 1. When an ideal lever of class first has the effort arm shorter than the load arm, both its mechanical advantage and velocity ratio are less than 1. Such levers are used to obtain the gain in speed because the velocity ratio less than 1 implies that dl is greater than de. That is, the displacement of load is more as compared to the displacement of effort. For example, a pair of scissors whose blades are longer than its handles is used to cut a piece of cloth or paper so that the blades move longer on the cloth or paper when the handles are moved a little. A long handle oar used for rowing a boat by a single person acts as a lever of class first as shown in figure. The point at the edge of the boat at which the handle rests acts as the fulcrum F. The boatman applies the effort E at its one end by keeping the effort arm shorter than the load arm so as to give a large movement to the blade of the oar to push water, that is load L, back through a longer distance, that is gain in speed. The force of reaction exerted by water on the boat moves the boat forward. Its mechanical advantage is less than 1. Two, class second levers. In this type of levers, the fulcrum F and the effort E are at the two ends of the lever and the load L is somewhere in between the effort E and the fulcrum F as shown in figure. The load and effort are on same side of fulcrum but in opposite directions and the effort arm is always longer than the load arm. Therefore, from equation 10, MA, mechanical advantage, is always greater than 1, and since in an ideal machine MA is equal to velocity ratio, hence VR is also greater than 1. Thus, the mechanical advantage and velocity ratio of class second levers are always more than 1. In other words, a class second lever always acts as a force multiplier, that is, a less effort is needed to overcome a large load. For example, in a nut cracker, a hard nut is broken by applying a small effort. Examples: a nut cracker, a bottle opener, a wheelbarrow, a lemon crusher, a paper cutter, a mango cutter, a bar used to lift a load, a door, raising the weight of the human body on toes,